This video is about electrical transformers. The purpose of a transformer in an electric circuit is to change the voltage level. As we'll see, transformers only work in AC circuits. So how do they work? Fundamentally, they use the principle of Faraday's law. I'll demonstrate this with the following setup. So here's an iron bar, and then I'll take a wire and I'll wrap it around the left side, and I'll connect those wires to an AC power supply, and then I'll wrap another set of wires around the right side, and then I'll connect a load to those wires. And then as a matter of terminology, I'll call the wires wrapped around the iron bar on the left side where the power supply is the primary winding. And then we'll call the wires wrapped around the right side on the load side the secondary winding. And now let's see how Faraday's law applies to this scenario. So because it's an AC power supply, the voltage is changing, and it changes sinusoidally in this case. So because that voltage changes, the current in the primary windings changes sinusoidally as well. And I'll label that current I sub P for the primary current. And so now we have a current in a coil, and it makes a B field, and I'll call that the B field on the primary side, which actually goes all the way through to the secondary windings, but I'll just show it this far so the picture doesn't get too crowded in a minute. And so because the current is changing, that B field is changing. And so because that B field is changing, then the flux in the secondary winding is changing. And so per Faraday's law, if we have a changing magnetic flux, then that induces a magnetic field in that coil. So this is the magnetic field in the secondary winding, which I'll add to the picture. And so then there is an induced current and EMF in the secondary winding associated with that induced B field. And so I'll add those to the diagram. And just to complete the picture, I'll add the voltage to the primary winding as well. So the bottom line then is this. A changing voltage on the primary induces a voltage on the secondary. And as it turns out, if the primary voltage is sinusoidal, then the secondary voltage is sinusoidal as well. Physically, when transformers are made, the iron core is typically made into a loop. The iron core, by the way, is there for a couple of reasons. One is it just gives you a convenient place to wrap the wires around, but then the other thing is it does carry the magnetic field, and so that enhances the effect of the flux changing and producing a voltage on the secondary side. So if the iron core is looped around, then a common design for a transformer would be like this. So this is the iron core, and I'll wrap the wires around the left side, and I'll connect that to the AC power supply. And so that will be the primary winding since it's connected to the power supply. And then I'll wrap wires on the right side as well and connect that to the load. And so that will be the secondary side. And then I'll label the key variables, which will be the primary and secondary voltage, and the primary and secondary currents, and then the number of turns or loops each winding has. As we'll see, the number of turns in each winding determines the relationship between the voltages and the currents on the primary and secondary sides. We can derive the relationship with Faraday's law. So here's Faraday's law on the primary, so we'll give everything a P subscript for the primary, where I've just written the EMF with delta V sub P. And then I'll write Faraday's law for the secondary as well. Now both sides experience the same change in flux, so these two terms are the same. So I'll solve the top equation for that term, and I'll plug that into the bottom equation, and then I'll rearrange it as a ratio of the voltages to the ratio of the turns in the windings. So that's our first equation for a transformer, just telling that the voltage levels depend on the ratio of the number of turns in the windings. Now thinking of power transfer in the transformer, ideally no power is lost in the transformer, and so because of energy conservation and therefore power conservation, the power on the primary is equal to the power on the secondary. In reality, some power is lost due to heat and vibration in the transformer, but as a general rule, we can neglect these losses. So the power into the primary equals the power out of the secondary. And now combining these two equations, we can get the relationship between the currents. So here's a little derivation starting with power conservation and replacing power with I delta V. And we can rearrange that as a ratio of the currents. And so from our first equation, this ratio is equal to a ratio of the number of turns. It's just inverted from the way that we wrote it. And so the result of that gives us our third equation. So notice that the current equation is basically the inverse of the voltage equation. From these equations for voltage and current, we can make the following observation. The side of the current with the greater number of turns has the greater voltage, but the smaller current. So if a transformer is used to increase the voltage, then it decreases the current. Or conversely, if a transformer is used to decrease the voltage, then it must increase the current. As a matter of terminology, we call a transformer that's used to increase the voltage a step-up transformer, which just means the voltage on the secondary is higher than the voltage on the primary. A step-down transformer is used to decrease the voltage, which means the voltage on the secondary is lower than the voltage on the primary. And then the last thing I want to show you is a schematic representation of a transformer when we draw it in a circuit. So this is basically the symbol for a transformer. Very often there are two lines down the middle to represent the iron core. And so if we connect the right side of this transformer to the power source, then that makes that the primary winding. So we give the voltage, current, and number of turns P subscripts. And so we'll connect a load to the other side. And so this is the secondary side, and we'll give all of these variables S subscripts. Well, that's it. There's an example on Moodle applying these equations, and that's the end of the video on transformers.